So if we look at equilibrium from the perspective of a gaseous relationship where all of the reactants are gases and products are gases, we can also look at equilibrium from the perspective of the change in partial pressure. All right, the total pressure of the mixture of any gases is the sum of each of the partial pressures, the pressure exerted by each gas individually. Okay, so we can calculate Kp just like we would Kc, Kc being concentrations, and we've talked about dealing with concentrations and looking at what that equilibrium point is if we know the concentrations of each thing at equilibrium. Now we can also look at, well, if we know the partial pressure of each component at equilibrium, then we can also calculate the equilibrium constant from the perspective of pressure. And sometimes that's going to turn out to be the same value as if we were doing concentrations, but not always, because it's dependent on how many moles of gas total we start with and how many we end with. But let's just look at the calculation component at this point. So if we have a reaction, here's the same reaction we looked at before. Ammonia, production of ammonia. So if I have nitrogen gas and hydrogen gas reacting to make ammonia, some of that ammonia is going to decompose back into nitrogen and hydrogen gas when it reaches equilibrium. At a given temperature, not necessarily the same one in the earlier video example, but at some certain temperature, the partial pressure at equilibrium of the ammonia is 3.1 times 10 to the negative 2 atmospheres, the nitrogen 8.5 times 10 to the negative 1, and the hydrogen 3.1 times 10 to the negative 3 atmospheres. All right, so each of those well less than an atmosphere of pressure. Set it up the same way. Products over reactants. Raise each thing to its coefficient as an exponent. When you plug that in and do all the math, when I did the math, I get a K value, which is 3.65 times 10 to the negative 1. For this given temperature, it will shift with temperature because you know that pressure is temperature dependent. Okay, so it matters what the temperature is in terms of calculating based on pressure. It turns out that that also might impact the kinetics of the reaction so that the equilibrium based on concentration will be different at different temperatures. Okay? How are the two Ks connected? Well, the relationship is summarized this way. Kc being K, as we talked about before, the equilibrium constant based on concentration, and Kp, concentration, the equilibrium based on, equilibrium based on pressure. So the equation that kind of connects them is the equilibrium based on pressure is equal to the equilibrium based on concentration times the two things that impact pressure, the gas law, universal gas constant, and the temperature, but also how the number of moles of gas change. So if I end up with more or less moles of gas than I started with, then that's going to impact the overall relationship between concentration and pressure. So it's always the delta N is always the moles of product, gaseous product, minus the moles of gaseous reactant. Here's the thing, when the moles are unchanged, and I'm talking about total moles here, not the moles of each species. When the total amount of moles going in and coming out that are gas are the same, it turns out that the equilibrium based on pressure and the equilibrium based on concentration are the same. And here's the mathematical proof. Let's look at an example, different example. If I'm combining hydrogen gas and fluorine gas to produce hydrogen fluoride gas, and then it decomposes, notice I have two total moles of gas, one of hydrogen, one of fluorine, but two total moles of gas to begin with. I make 2 moles of gaseous product, so 2 minus 2, product minus reactant, is 0. Well, anything raised to the 0 power is 1. If I plug that into my little equation here, it turns out the two things are the same. Okay, so we can calculate equilibrium if we know the equilibrium values of concentration or pressure if they're gases, only if they're all gases. Okay? So if we're talking about a gaseous phase reaction, if we know concentrations, we can figure out what's the equilibrium constant if we have those concentrations at equilibrium. We could also go from the partial pressure exerted by each gas when the reaction is at equilibrium to calculate that. And the relationship between them is a function of the gas constant times temperature raised to the difference in moles between product and reactant. And if the total number of moles doesn't change, well, the value for K remains the same.